bit. Um, so we're recording. Um, so today we're going to be talking about the buck converter, right? And this is for this modeling and control of power electronics course. So we'll be meeting every week. I kind of forgot to put the schedule, but yeah, let's talk about the schedule real quick. So for those of you that are kind of new to the group, I've just been trying to give weekly talks on different topics. And I think this was in the email that Yvonne had sent out. But here's kind of an overview of the schedule of topics that we've got for this quarter. Right, so this week we're talking about the buck converter. Next week we're looking at the boost and buck boost, and so on and so forth. Um, this is still kind of up in the air. This is what I'm hoping to cover, but we'll see how it goes as we progress through the quarter. Um, so with that said, I also want to share the Discord link for those of you that aren't in the Discord and might be interested in joining the Discord. So let me get that link into the chat here. Um, you're welcome to join or not. It's up to you, really. And so with that, I think we can go ahead and get started with the talk. Feel free to stop me at any time if you have any questions, but let's just walk through these slides. So I guess for those of you that don't know me, which I guess is just Harrison really, but for those of you watching the videos in the future, my name's RJ. I'm a grad student in the master's program in electrical engineering. I've been in the master's program for about 3 years at this point, and just working on my thesis and doing some teaching on the side. So this quarter I'm teaching EE 361. So if anyone's interested in like volunteering to kind of like TA in the class, you're welcome to reach out to me and we can get that set up. So that's the electronics class for the other engineers, mostly mechanical, some biomed people in there. But we do a lot, we cover a lot, and it's a lot of fun. So here are just some objectives of our talk today. We're going to be talking about the need for power conversion, and we'll be looking at the buck converter. We'll analyze operating principles at a very high level, and then we'll learn how to simulate and model the buck converter and kind of look at reference design as we get there. So first off, we're starting off, with the need for power conversion. So in your circuit theory class, you learn about this idea of a voltage divider, right? So this is two resistors. You got your input voltage, and your output voltage is some fraction of the input. Um, and you also learn about this maximum power transfer theorem, right? And so when the resistance of the source matches that of the load, you obtain maximum power transfer, so to speak. But this is really bad, right? So this is only 50% efficient, right? Because you can imagine, you've got the same voltage drop across the load resistor, as the source resistor, because you got the same current flowing through them. And so that amounts to 50% efficiency there. Um, so here I've got some statistics that I kind of just pulled online. So we got 4.2 billion kilowatt hours projected energy consumption for 2025. And, if we were using voltage dividers all over the place, that would be 2.1 billion kilowatt hours lost. And that would come out to about $3.36 billion just in lost energy. And so you can imagine, around the world, we need efficient power conversion because we don't want to be losing all kinds of money just to inefficient conversion. So the buck converter is a simple way to create a more efficient voltage divider. Um, So this is the topology of a buck converter. Just a very simple, the most simple buck converter that you can find. So here we've got the voltage source. I think this is like the European model or a diagram, symbol for a voltage source. And then here we've got a switch. This is called the flyback diode or some kind of rectifying diode. And then you have an inductor and a capacitor, and then this last thing here is just modeling the load. So the main idea is that we want to apply a voltage, right? So we're going on, off, on, off very fast to this, right? The switch is applying the voltage on and off. Um, and this inductor and capacitor here act as a low pass filter, right? So this kind of structure you should be somewhat familiar with. It filters out high frequency content, which we should be familiar with. The square wave, it's changing very fast. And our goal is to try to smoothen out that change so that at some point, the output voltage across this capacitor, it'll go up, it'll go up, it'll go up, it'll go up. And at some point, it'll level out to a relatively steady voltage. And so then there's this harmonic component that we can't really completely get out due to the nature of, these filters not being ideal and so this is called the ripple, right? And so this ripple, we'll talk about it a little bit later, but it's usually an undesirable quality of, a DC voltage. So we can't make perfect DC, but we can get pretty close. And the buck converter does a good job of, you know, transforming this input voltage in a relatively lossless manner, right? So we'll have two forms of power loss. There will be some conduction loss due to this inductor, right? So this inductor is effectively a wire and it's got some current flowing through it. It's got very little resistance, but just because it has current going through it, you know, there's going to be some power loss in this inductor here. Likewise, with the diode, there will be some current flowing through it and it has some non-zero forward voltage drop. And because of that, it's going to have some power loss associated with it as well. There will also be switching losses, which we'll save for another discussion, I think. Um, so I make the statement with one switch. There are two operating states of the buck converter. We'll see later that sometimes this diode is replaced with another switch. Um, but the main idea is when the switch is on, right? So we have energy flowing through this inductor, right? So the moment we switch this on, current starts to flow through the inductor, and then that current also builds up the voltage in the capacitor and also drives the load a little bit. But in this off state, all of the energy is coming from this inductor. This inductor is supplying both the capacitor and the load. And then, to keep that momentum going, we have this diode to keep the circuit closed here. Um, so I think we'll take a look at the waveforms a little bit, but this is the main idea, right? So we have the on state and then we have the off state where, energy is starting to flow just due to these passive components here. So the buck converter is a type of pulse width modulated DC to DC converter. Um, and so it turns out that the buck converter output voltage is proportional to the duty cycle. And so I've got this link here, and I think it takes you to kind of like the derivation if you're interested in it. Um, if you're really interested in learning a lot more about this, Coursera has a really good power electronics course that does a good job of covering a lot of the basics of these topologies that we'll be talking about today. But anyways, so this is a really basic formula that relates the duty cycle to the input and output voltage, right? So if I've got 10 volts in and I got 50% duty cycle, then I should expect 10 times zero point 0.5 at the output, which would be 5 volts there. So that's just an example of, how to apply this formula. So apart from efficiency, another good measure for power conversion is load regulation. And so this load regulation, concerns kind of like how much power our load is consuming. And so that's often modeled as some kind of current source. So here we have a current step on the bottom plot. And as that current steps up, you can see that this is going to be the output voltage at the top plot here. The output voltage starts to fall down, and then it should recover back to its little steady state. Um, and so you can see the different stability, your typical control stability waveforms here, involving, step responses. Um, so, and then there's, similarly, we have line regulation. So when the input voltage changes, we want to still be able to maintain a constant output voltage. And so I didn't put another image here because it would look very similar, but it would be, a step in the voltage, up or down. Um, and so that's another thing that we like to look at when we're designing power converters. And so the load is often dynamic, and we need some form of control to maintain a regulated output voltage, right? So for example, the USB standard is 5 volts, and maybe you have some kind of input voltage that swings from 15 to 20 volts or so. Um, and so I guess sorry, so that would be a case where the input voltage changes, but you might imagine the moment we attach maybe like a whatever we're charging maybe with the USB port, well, the moment you attach that to the load, right, that'll be your load and it'll start drawing some current. And so the moment that that changes, our duty cycle will need to change because our output voltage is going to start to dip, right? So going back to here, the moment that current steps up, our output voltage will likely go down. And as a result, we'll need to modulate the duty cycle to account for that change, right? So it's going to start requesting more and more voltage until it reaches its steady state there. And so this is an example of what a very simple control system might look like, right? So you have some kind of sensor gain, and then you have your reference input. Um, you get your error signal, and then we get some kind of compensator. This is usually, some kind of PID compensation. And then, with that, you use your pulse width modulator to drive the gate of your switch here, right? To turn it on and off, depending on how much more voltage you need. Um, so, of course, we like to look at simulations. This is a very nice, I don't know if you guys are familiar with Falstad.com, but they have a pretty nice circuit simulator app. And just for reference, this will be very useful for those of you that are taking 409 in the future. It has pretty much everything you might need. But one thing that they have that is good for us today is the buck converter. So here we have the buck converter. You can see it's got 5 volts in, and I believe. So we can play around with the duty cycle here. So right now it's set to 72%, um, which means that it should, level out at some point to 5 times 0.72, which is about 3.6 volts. And you can see it's oscillating kind of like about that. Um, so that's just one nice little tool that we have access to here. Um, but I won't talk too much about Falstad. It's nice for getting a sense of how the circuit operates here, but other than that, it's kind of hard to work with. So there's that. I think that's the next slide. And so I had mentioned Ripple before. For those of you that have seen, some kind of rectification, in this case, it looks like a full wave rectified signal. You often study ripple in the context of these kind of waveforms. Um, but anyways, so whenever we're trying to create, some kind of DC fixed output voltage, like 5 volts or something, well, we'll almost certainly have some kind of ripple just due to the fact that we have this switch that we're modulating on and off, right? So like I said before, this LC structure here is a low pass filter. We're trying to get rid of the sharp edges of that square wave, but of course we're going to have some kind of residual um, harmonic component. Um, and so the more capacitance that we have, obviously, we'll have less ripple, less voltage ripple at least. But it comes, with the trade-off because we really want to achieve this high power density. We want to pack in as much power as we can into as little space as possible. And so this becomes a really hot topic in research, right? So if I go just to IEEE, and if I just look up power density papers that have been published in the last year or so, you could probably, I bet you it's on the order of 1,000 or so. So if I just look up power density and then maybe I just want this year only. We can see what we get here. Right, so just this year we've got 2,400 papers on that mention to some extent power density, right? And so this becomes a very hot topic. Um, you utter the word power density and people will throw money at you probably in the future. So keep that in mind. Um, so Texas Instruments has a very nice document on how to calculate buck converter power stage. And so if anyone ends up taking EE411 with Professor Tawfik, he has you guys design kind of like a buck converter to step down voltage from his solar panel and to charge his cell phone. And so this is a very useful document for, if you ever want to step through and calculate what kind of inductance you need, right? So really what we need here is an inductor, a capacitor, a diode, and some input capacitance. And this input capacitance usually depends on what kind of chip you're using for this switch to drive the switch, or to realize the switch rather. And so this does a good job of outlining all the steps to calculate those things. But if you're lazy, we've got this tool called Webench or Webench. And so you can use this to actually create your own buck converter. You specify input voltage, output voltage, and how much power you want effectively by specifying the current as well. And then it spits out a bunch of designs. So just as an example, let's say we've got this 10-watt solar cell, and so I actually found one online. I think I might buy this just to experiment with it. Um, So let's say we have this 10-watt solar cell, and it has voltage between 15 to 20 volts. So I found that down here. So it says the optimum operating voltage is 18. I'm just gonna call it 15, and then the open circuit voltage is 20 volts. So without anything attached, it's got 20 volts on there. So we design in some headroom there, get 15 volts down up to 20 volts. And then that short circuit current is also pulled directly from here, right? So if I were to short the voltage terminals of this solar cell, then I should get about 0.58 amps. Um, so then, let's just say we want to design with those parameters, bibbidi bobbidi boo, WebEnch spits out 436 designs, one of which, you could build up and you can see, let's see. I think I had it pulled up. Yeah, so here's the first one that it spit out. And, if you wanted to buy the components to build this up, it's only $1.50 plus probably eight or $9 shipping. Um, but yeah, so this is kind of neat. Um, let me see what I had in the slides here. Yeah, so let's walk through kind of this Webench tool here. Um, So I've got this design already saved here, but I'll just show you the process of making a new design. So we specify what we want, and then we just hit view designs, or you can, have some non-advanced parameters here, and you can specify, your design considerations. So maybe we want a really tiny converter. You can go small footprint, you can go high efficiency, whatever you want, really. So it's a very nice tool. You design it, and it spits out all these. But I'm just going to go back to the one that I already have. So here's the one that I've got. Um, I think you're able to spit out a whole design report, which is kind of incredible. So I think it runs a bunch of simulations and it spits out a report that looks like this. So it gives you the circuit, it gives you the whole BOM, right? So whatever parts you might need to build this thing, it shows you kind of like some characteristics of all the different parts, and then efficiency. So this is a big one. You can see it reaches up to about 96% efficiency, so that's pretty good. Um, yeah, I mean this thing that would otherwise take you a pretty long time to generate on your own, you can do in seconds with this tool, which is nice if you're designing something relatively basic, right? So obviously this isn't really good for like a senior project, so to speak, but for a 10-week quarter where we're building something in Tawfik's class, this was a pretty helpful tool, So again, if you ever take 411 with Tawfik, like this is a lifesaver. And it actually worked out. So we built something similar to this, and it worked. So pretty cool tool. Um, so it tells you the frequency, which is a pretty important thing to consider if you're going to go off and do your own simulations, especially, which we're going to be talking about today a little bit. But first, I want to show you what kind of simulations that they provide here. And it looks like simulation's not enabled for this design, so that's interesting. I haven't seen that before, but we'll try simulating it on our own anyway. Um, oops. So going back to here, this is just Webench again. Um, Texas Instruments also has a very nice reference design for microcontrollers. For those of you that were, attending my talks last quarter, we're looking at the C2000 family of microcontrollers. And so this reference design actually uses that C2000 microcontroller. Um, so here you can see it's called the C2000 Digital Power Booster Pack. And, if anyone's interested in playing around with this, I've got one sitting around here at home. Um, so it's pretty nice. It's what we call a synchronous buck converter because instead of that diode, in the path from ground to this little node up here with the inductor, we replace that with a switch. And so the proper terminology is this is a low side switch because it's referenced to ground, and this is the high side switch up here. So if you ever
Wait, I had a
hear that,
question.
yeah, what's up?
Um, Whenever I had a buck converter explained to me, they always said a switch. So I was thinking in my mind, oh yeah, yeah, just a little switch flickering. But now I'm seeing you're saying MOSFET, switch. So how many like
Yeah,
different types of switches are there that, and is there like potential upsides and downsides to using one switch over another?
that's a good question. Typically they're MOSFETs, and I think that's because, BJTs are mostly used for amplification of current, I think, from what I've seen. Um, so yeah, I mean, whenever you see power switches, at least, they'll usually be MOSFETs, or recently, there's been a lot of GaN FETs. I don't know if you've heard of GaN FETs, but these are a hot topic right now. Gallium nitride and um, silicon carbide. Uh, so GaN and SiC are becoming, predominantly the hot topic of power electronics research, and that's mostly due to their properties of they basically switch a lot faster than these regular MOSFETs that we've got, silicon MOSFETs. I think that answered your question, right?
Yeah,
Mostly.
thank you.
Yeah. Yeah. Um, so yeah, so again, this is a synchronous buck converter that they've got implemented on this board. And one thing I like to note about these TI reference designs is that they've got the full schematics open source. So if you ever are interested in kind of just building what they've already pre-made and they're selling, um, I don't know how much they're selling it for, but I don't know. It's probably on the order of $100 or so, but you could easily build this for less than $100. Um, so they've got open source schematics, which are really nice, especially if you want to try to design something similar, but not exactly what they've got. And then they've got the whole design reference to walk you through, if you buy this specific thing, how to test it out and um, kind of explore different modes of control. Um, right. So this is all powered by a microcontroller. It'll sit, I think they might have an image of it somewhere. Sorry if this is making people dizzy. Yeah, so it kind of just this red block here is their C2000 microcontroller, and it just sits on top of this little synchronous buck converter that they've got going here. So this is a really good reference, especially if you are interested in learning about microcontroller programming. Um, obviously, since you need the microcontroller to run this buck converter, it's got all of the code open source as well. I don't know that it's on this. Yeah, so it's not available on these design files, but I know in Code Composer Studio, which is their IDE here, you're able to go to their little resource explorer and find the buck converter. And I can, if this is, if I can find it real quick, I'll show you. But if I can't, that's probably okay. So it's probably here and probably maybe here. Oh, so that's not it. And again, so they have a lot of these kind of like reference designs that we'll be talking about throughout the quarter. Um, so it's all open source designs and code. It's a really good resource for learning. You could spend years, learning about this stuff. So here's an example of, their buck converter code. It's a whole project file, so, it would take a while to kind of understand everything that's going on in it. Just this one file is about 600 lines. So if you've got like 10 weeks to study a buck converter, you could easily do so. So that's just one thing I like to kind of like point out. I don't think there's anything specifically in this that I want to cover today, just because it's a 57-page document, and obviously we don't have that much time. But again, if anyone's interested in playing around with it, I've got the microcontroller and this booster pack laying around, collecting dust. So there's that. Um, and then so obviously when you get to designing moderately complex systems, the automatic tools that are available online are not always sufficient. So you'll often have to simulate your system on your own. For example, you can use Simulink. I know another tool that's been gaining a lot of traction is Plex. And I know Professor Poon at Cal Poly is a big fan of Plex. From what it seems like, it looks like a lot of his students are playing around with Plex. So Plex is another simulation tool. They also have an extension for Simulink, which is nice, but at that point, why not just use the standalone Plex app? The nice thing about Plex is that they've got a whole simulation environment, and they've also got these things called real-time boxes. I think that's what the RT stands for. I mean, it says real-time simulator. So this is nice, if you're designing power electronics and you want to simulate the behavior of it. I haven't used one personally, but from what I heard, they seem like a good tool. They are on the order of like $50,000. So, if you if you get a chance to work with Professor Poon or get a chance to use one, you should really appreciate that opportunity because they're not cheap, and but neither is MATLAB and Simulink. So yeah. So Plex, I'm going to be showing you guys how to use Simulink just because we have, an academic license of MATLAB and Simulink. Unfortunately, we don't have Plex. I know you can request one if you're taking a power electronics course, with Jason. He gives like a link to get a license for like a month or something. But so anyways, let's build this thing up in Simulink. So I'd like to preface this by saying I haven't done this yet. So this should be fun. I did find an example of a buck converter just in Simulink here, and I found it to be not great. So let's actually just look at this first. So here's their buck converter. Um, they've got this little subsystem that does whatever, and it looks like they're using insulated gate bipolar junction transistors. So I guess they are using some sort of BJT, which is interesting. So I personally don't know the trade-offs between all the different switching devices, but it is a good question. Um,
Fair enough.
yeah, so looks like they've got a piecewise constant resistor here. I don't know why that's being commented out. I'm trying to move this, whatever. Um, so I guess they've got this controlled resistant resistor, which is interesting. I don't think I've seen that before. Um, and they've got a controller, so it's got a reference voltage that's being sampled. I don't know. It's got a reference voltage. Got this voltage controller, which is just really just a PI controller. Um, and then they got this PWM generator. So I don't know. It's kind of interesting. I don't really like how it's made. Um, but actually, maybe we'll just try to play around with it. So here's they've got a little script to actually plot the code. Um, and I'm not sure that it opened. So here, you can kind of see it looks like it's doing a step of some sort. I just don't like it because you don't really know what's going on when you run it, right? So there's for some reason the output voltage drops and then it goes up here. Like who knows what's happening there. Um, I mean, I guess you could look here, right? And so it's doing a step at 0.15 seconds. So that must be here. And so if we kick up the resistance, it starts at 2, goes up to 3, then we would expect the output voltage to go up, because more resistance means less current. So less current means, the voltage should start to go up there. Um, but anyways, so actually maybe this does a fair job of kind of simulating the buck converter from a first glance. But what I don't like about it is, first off, it's hard to change, right? So like imagine we want to use okay, so I guess it has the option to choose a MOSFET. Um, I don't know. I'm trying to pick apart this thing, but I just can't. So I'll just show you how to build one up, hopefully from scratch here. So I'm just gonna close this first off, right? Because at some point, uh, they won't have examples of what we're trying to build, just from that search window. So we'll need to learn how to build them up from scratch. And so hopefully I can do that. So we'll get to see me struggle a little bit potentially. So I'm just going to start one. I'm just going to save this as buck. And we're going to try to recreate this guy. So here we've got our input voltage. And so we need a means for controlling the input voltage. So maybe we want a controlled voltage source. And so let's see if I can do this in 10 minutes. That would be kind of impressive. So here we've got a controlled voltage source. Um, I'm going to call it VG. I don't know why a lot of books call it VG. I'm assuming it's voltage of the grid, but if anyone knows, let me know. It'd be interesting to find out. And so I'm going to use a MOSFET, this ideal switching MOSFET. So this will need a gate drive signal, and then it's actually going to go this way, right? And the way that you know which way that it's going is because when it's conducting, we want power to flow from the source into, towards the load. And this is a kind of like This diode here kind of should point in the direction that we don't expect current to be flowing there. I think. Um, Let me take a look at this actually. So they've got it. I guess they don't have one. Anyways, um, so they've got this guy like that. Yeah, so let's just go like that. So I think, yeah, so from what I understand, this diode should be pointing in the direction that current, we don't want current really to be flowing. Um, but I could be wrong there. So we'll just go with that. We'll also need the inductor. So we'll grab an inductor, need a capacitor, and we'll need a resistor. So I think they had some kind of controlled resistor thing, but I think I'll just do a current source. So this is a controlled current source. So let's hook all this stuff up here. And so it's interesting, that I'm using a current source as the load. Typically, when you're testing power electronics, you want to test as different loads, um, as different types of loads. So whenever you have kind of like a DC, it's called a DC electronic load, and these are really expensive too. You can usually specify if you want constant current, constant voltage, or constant resistance mode, right? So CC, CV, CR, and I guess this might be constant power. Um, so it's just one thing, another thing to keep in mind when you're modeling electronics, power electronics. So, in a perfect world, we would have the same operation, whatever the load is. And I would assume with this really basic converter that we should have, fair chance at, good behavior with just a constant current load here. So let's go back to here. So we got 10 microhenries for the inductor. Let's do 10e minus 6. And so you can model a lot of parasitics as well, such as like the series resistance, parallel conductance, a lot of different things. Um, and so for the output capacitor, we want 47 microfarad. So we'll do 47 E minus 6. And then for now, um, so I think we'll need a Simulink to PS. So this little thing here just converts the signal from a Simulink to the power systems, or sorry, physical systems. Um, Whatever the PS toolbox is there. So we'll just start off with no load. So we'll be drawing 0 amps here. And then um so for now let's just do a constant voltage too. So let's just fix it to the nominal, which I think was 18. So here's our nominal voltage. Um, it's kind of annoying. You'll need to get a voltage sensor whenever you're looking at the signals here. So we'll get a voltage sensor. Um, we'll look at the output voltage, and then you'll need to convert PS to Simulink to kind of look at it on an oscilloscope here. So I'll get a scope block. And so we'll look at the input voltage on channel 1 of the scope here. So I'll plot this guy. And then we'll look at kind of like the output voltage on channel 2. So that's not very nice. Let's try that. Okay. So here's our setup. Um, the next thing we'll need obviously is some kind of gate drive signal to the MOSFET. Um, so I'll go ahead and get another Simulink to PS converter and we can explore. So I think there should be a square wave generator or kind of like a pulse generator. So here's a pulse generator. Um, so the MOSFET does have a threshold voltage, and I'm just going to set that to zero point 0.5 for now because this pulse is outputting with an amplitude of 1. And so here you can see we can change the switching frequency. Um, and so that was specified back here of the intended switching frequency, which is 400 kilohertz. So in order to get a period from that, we just take 1 divided by 400 kilohertz. So that gives us our switching period. And I think I can change this pulse width real time, but for now, let's just set it at 50%. So with this 18 volts in, um, I would hope to get 9 volts out, but I suspect that the voltage will just blow off to infinity because there's no load. And this is like unregulated. It's kind of just running in open loop here. So let's just see what happens because I don't actually know. Um, and of course, everything breaks here with 3 minutes left. Uh, oh, okay. So we'll need we'll need a ground. So that's called electrical reference. And moreover, we'll need this solver configuration. Uh, I don't really know what this is for, but you need to tie it to ground when you're doing power electronics. Uh, okay. So I suspect that this scope will kind of just go to infinity on the output voltage. But let's see what's actually happening here. So I can pause it and we can zoom in to see everything that's happened. And we'll probably want to label these guys. So I'm going to call this V in. And I'm going to call this guy V out. And then I'm going to kind of like set up the scope here a little bit better. So let's go to configuration properties. Um, let's have the time span be maybe 10 periods, so 10 by 400K, and we'll just have it wrap, so that's fine. Um, and then I think that should be fine. So let's see what happens here. So here you can see the output voltage starting to come up, and will it stop at 10? No, or 9. So it keeps going. And so now if I just crank this back to 0%, um, maybe 1%, it might start to fall. Or how about we just drive this thing at full load? So we can start to load this thing. So at full load, we would expect the current to be, so we've got 10 watts out, 5 volts out. So the current should be 10 by 5, so 2 amps. So if we got 2 amps, um, Let's kind of just see what that does. Okay, so the voltage is way negative. So, obviously this will take a little bit more time. You'll need to set up kind of like a PID controller. So for those of you that are interested in sticking around, this could probably take me another 20 minutes, but otherwise you're free to drop off, or if you have any questions, definitely just go ahead and stop me here. But I think I can do this. So we're gonna make a PID controller. Um, and I'm going to tap the output voltage, and I'm going to create an error signal by taking the sum. Uh, sorry, take the difference. No, okay. Yeah, so I'll take a sum and I'll take a negative sum. So I'll change this one of these to minus. So I will take my output voltage and subtract it from a reference, which I'll just make constant. And so actually, I think we want to be subtracting the output voltage. And so we want to regulate to 5 volts here. Um, get our PID. And so with this, we should be able to modulate the pulses. And so I think they actually have a pulse width modulator block here. So yeah, actually, this might take a little bit longer because, I mean, so what we would need to do is create like a ramp reference generator, and then from there, um, use the PID controller to modulate that signal. We can't just have this pulse generator directly. Um, so I think I'll stop there. I'll try to finish this up and kind of present it next time. But yeah, so any questions on anything?
So the PID controller, I'm understanding that if the voltage goes higher than expected, then it's going to like decrease the duty cycle so that it goes down and then increase goes up, and I'm assuming hopefully reaches
Yeah.
a steady state. Gotcha.
Yeah, that's exactly right. So nominally, right, we'll have a duty cycle. Um, if we're trying to put out 5 volts from 18 volts, our duty cycle is going to be 5 by 18, whatever that is. So 5 by 18, so about 20, 27, 28%. The moment that that gets loaded down, the voltage is going to decrease at the output. And so in order to compensate for that, our duty cycle is going to need to go up. Yeah, so yeah, that's exactly it.
Man, I thought it
So,
was just gonna work out of the box.
yeah, right? Can only wish.